Swayam Prabha. Digital India. Educated India.
So, applying a material balance to the feed tray or the feed location gives us this relationship L bar minus L by F is equal to H G minus HF over H G minus HL, and this we denote as some quantity Q. So now let us look at what this equation means. As I said, it's basically a mass balance. This factor L bar minus L by F is basically the fraction of liquid present in the feed. So L bar is the liquid flow rate in the exhausting section, and L is the liquid flow rate in the enriching section. So that difference in the liquid flow rate is supplied by the feed. So therefore Q kind of defines a fraction of liquid present in the overall feed. And we can also write from this equation that G bar minus G is also related to F times Q minus 1. So from these two equations, we can find out what is the change in the molar flow rate of liquid L bar as well as the vapor flow rate, that is G bar, once we know the value of F and Q. And generally Q is obtained from the other equation relating to the enthalpies of the various streams. So we have another independent equation for Q determining Q, Hg minus Hf by Hg minus Hl. So in this equation, Hg here is the enthalpy of saturated vapor at the dew point corresponding to the feed composition. So the feed will have a composition ZF. Corresponding to that, from the TXY diagram, we need to find the dew point temperature. At that temperature, we have to calculate the enthalpy of the saturated vapor, which is what Hg refers to. Similarly, HL, this is the enthalpy of saturated liquid at the bubble point corresponding to ZF. So corresponding to the feed composition ZF, we need to find the bubble point. At that particular bubble point, the enthalpy of the saturated liquid is HL. Whereas HF, this is the enthalpy of the feed. This is enthalpy of the feed. So if we can calculate the enthalpy, these three enthalpies, we can obtain Q, and if we obtain Q, we can find out what is the change in the liquid flow rate as well as the gas flow rate. So essentially these are all set by the material balance applied to the feed tray. Now you may recollect that the absorption column is looked into two parts. One is this enriching section above the feed tray and the exhausting section below the feed tray. At the point of the feed location, the flow rates are changed. Because the flow rates are changed, the operating line slopes will also change. So in any distillation column design, we will have two operating lines. One is the enriching operating line, another is exhausting line operating line, and these 2 points will intersect at some point of time, and that point should correspond to the feed locations. So now the next task for us is to look at what are the possible points in which the two operating line can intersect. This basically leads us to the discussion of the Q line. So Q line is basically the locus of intersection of enriching and exhausting section operating line. Okay, so if I have to show this schematically, so this is the 45-degree line, and this is your equilibrium line. Y is here, X is here, and for a given distillate composition XD, we can draw the operating line for the exhausting section. Similarly, for a given residue composition XW, we can draw the exhaustive line operating conditions. So you see that there is a point in which they intersect. The slope of these lines depend on the flow rates of liquid and the gas. What we are going to do is, we are going to look at what are the possible points in which the two equations will intersect, and we can obtain this by simultaneously solving the two operating lines. So let's write the equation, the operating line equation for the enriching line. So the enriching operating line equation is Yg is equal to Lx plus dxd, and for the exhausting line, we write Yg bar is equal to L bar x minus W xw. So here we can solve these equations to get the intersection points. So first what we will do, we will subtract the two equations. Subtract so we get G bar minus G times Y is equal to L bar minus L times X minus W xw plus dxd. So we are subtracting first equation from second equation, so then we get this. Now if you look at this particular quantity, and this particular quantity is nothing but the is something that is related to the overall material balance. So if I do overall material balance for the entire distillation column, so this is F times ZF is equal to W times XW plus D times XD. Okay, so now for this term we can replace with F times ZF. Now solving for Y, we get this. Now what we can do, we can replace this L bar minus L and G bar minus G using this definition of Q that I mentioned here. Recall that we have defined this Q and how Q affects L bar minus L. So I can write L bar minus L equal to FQ, and similarly G bar minus G as F times Q minus 1. So this is F times Q, this is F times Q minus 1 times X, this is F times Q minus 1 ZF. So this is something that we denote as the Q line. So the Q line is nothing but these are the set of points in which the two operating lines will intersect, and we have obtained this by simultaneously solving the two operating lines corresponding to exhausting and enriching lines. Now if you look at this equation, we can actually even see how this equation will be represented in the equilibrium diagram. So this is a Q line, and it has a slope of Q by Q minus 1, and Q is something that can be obtained based on the enthalpy calculation, like I mentioned before. So once we know the Q value, we can find the slope of this line, and then this Q line can be shown. You can also see that if we substitute X is equal to ZF, from this equation we see that Y is equal to ZF, meaning the Q line will intersect the 45-degree line at ZF. Okay, meaning that if this is my equilibrium line and this is the 45-degree line, and then you can mark this point ZF, one end of the Q line will be in the 45-degree line, and then it will have a slope equal to Q by Q minus 1. Okay, and that's way we locate the Q line. So if I draw a Q line, for example, like this, so these are the set of points in which the two operating lines, exhausting and enriching operating lines, can basically intersect. Okay, so those are set of intersecting points. Now depending upon the values of this Q, we may see different kinds of Q line in the equilibrium diagram. So let's take an example of this. So this diagram kind of lists various possible Q lines. So here we try to show different possible Q lines. So here this red line here, this is the operating line of the enriching section, and this red line is the operating line of the exhausting section. Now these 2 points cut at this particular location, and so you see these different black lines, these are all related to different kinds of Q lines, and as I said, the Q line can have different slope, but they all will start at the 45-degree line corresponding to ZF. So the way that we should locate the Q line is first marking the a point on the 45-degree line corresponding to the feed composition ZF, and then finding out what is the slope of this line, and the slope of the line is given by Q by Q minus 1. And if you look at for example, if you consider Q is 0, okay, so Q is 0 basically would mean L bar minus L by F, this equal to 0. It also means that Hg minus Hf over Hg minus Hl is 0. Okay, it basically means that when Q equal to 0, we are not changing the liquid flow rate at all, which means the feed has to be totally a vapor or totally a saturated vapor. So that would happen if HF is equal to Hg. So this is what I say as that the feed has a 100% saturated vapor, and that is this line shown here. So this one corresponds to Q equal to 0. So when Q is 0, it means the feed is a saturated vapor, and that corresponds to a horizontal Q line. Let's say if Q equal to 1, this means that L bar minus L by F is equal to 1, which means all the feed is saturated liquid, and this HF would be equal to HL. Okay, the feed enthalpy is equal to the saturated liquid enthalpy, and all the feed is nothing but liquid, saturated liquid, and that corresponds to this vertical line, because here for Q equal to 1, the slope Q by Q minus 1 will be infinity. Okay, so this slope of this vertical line is infinity, so this corresponds to saturated liquid. So these are possible physical state for the feed. If you have a saturated vapor, the Q line is horizontal, and if it is a saturated liquid, it is a vertical. If you have a mixture, two-phase mixture of both liquid and vapor, then Q will be anything between 0 to 1. Then you may have a combination of liquid plus vapor, and that corresponds to this line. Sometimes we may have liquid below the boiling point, and then you will have a Q line which is little on the right hand side of this vertical line, or sometimes you may have a vapor that is superheated and that goes below this saturated line. Okay, so if the way to draw the Q line is to find out what is the value of Q based on the enthalpies, and then once we know the enthalpies, we can calculate the Q. From the Q we can get the slope of the Q line, and then we know one point on the 45 degree line, and then with the known slope we draw these lines. Okay, these are possible Q lines, and the Q lines are those which give the locus of intersection of the operating lines, exhausting and enriching operating lines. Now let's talk about how do we find out the location of the feed tray. Location of the feed tray. Location of the feed tray can influence the number of theoretical stages. So it is important to find out what is the optimum location for the feed tray, so that we can operate the distillation column at the optimal number of trays. So to illustrate this effect of feed location on the number of stages, we have taken some examples here. In this figure A, the blue line here corresponds to the equilibrium line, and this red line here corresponds to the operating line of the enriching section. This particular enriching operating line will be fixed the moment we fix the distillate composition XD and the reflux ratio. This line here is the Q line, and the Q line is fixed the moment we discuss about the, or we fix the feed condition, whether it is saturated liquid or is a saturated vapor or is it a mixture of the liquid and vapor. Based on the quality of the feed and the feed composition, the Q line is fixed. So you can see that this line DG, which is the line DG, is the operating line for enriching section. It meets the Q line at this point E. And since this Q line is a place where both operating line touch or intersect, the exhausting line will also go through the same point E, and the other end of this would be at the residue composition. So that means once we fix the residue and distillate composition and the reflux ratio and the feed, pretty much we know where this intersecting points are. Now in this particular situation, one can draw the staircase diagram to find the number of trays. So you can see here this is third tray, fourth tray, fifth tray, sixth tray, and then when we come to seventh tray here, suppose if feed is introduced here, we can use this enriching operating line to calculate the number of trays up to sixth tray. From seventh tray onwards, we have to make a transition from enriching line to exhausting line. So you can see that the seventh tray goes all the way to the operating line of the exhausting section, and from here onwards we continue the counting of number of trays. So in other words, depending upon where the feed is located, so here the feed line, feed tray is feed is introduced in the seventh tray. So we use the operating line for the operating line of the enriching section till sixth tray. From seventh tray onwards, we make a transition to the exhausting line. This is because when we introduce the feed, the flow rates are changed. Then the operating line will have to go from enriching section to exhausting section. Now, if you consider this case B, where the feed is introduced at the fourth tray, in this case we use the enriching operating line up to stage 3, and then when we come to stage 4, we make a transition to the operating line corresponding to the exhausting section. So you can see that up to 3 we are here. In the fourth tray, we go to the operating line corresponding to the exhausting section, and then we go on from here. Okay, so that means the feed location will demark the transition from enriching to exhausting operating line. And then you can see that depending upon whether we introduce the feed in the seventh tray or fourth tray here, the number of stages will be different. But if you ask what is the optimum location to introduce the feed, what we need to do is we construct the staircase diagram, and whenever we cross this intersection point, we take the operating line that gives the largest step size. For instance, let's follow this particular staircase construction. So this is third tray, and then when we come to fourth, here we have a choice. We can either stop here and then we make a transition to the exhausting line, or we can continue to go all the way to the enriching line. So among these two options, this line gives a bigger step, so we continue with the enriching line and then we go further, and then here we can either stop at this point or we can go down all the way here. So but we can see that this step gives me the largest step, so we make a transition to the exhausting line at fifth tray. From here onwards, we continue the staircase construction to the in the exhausting line. So here the feed should be then introduced in the fifth tray. The feed should be introduced in the fifth tray, and that's what we call as the optimal location of the feed tray. And another important thing is about the total reflex. So remember, reflex is something defined as the liquid that is sent back to the distillation column over, the reflex is defined as the liquid that is sent back to the distillation column divided by the distillate number of moles of the distillate, that is L by D. Now this reflex ratio is something that we design depending upon how much the flow rate of liquid that we want to operate. And if you look at the operating line, this reflex ratio R is very important quantity. For example, if I write the operating line for enriching section, and then for the exhausting section, So from here, the slope of this operating line is proportional to this L by G. So this is given by R by R plus 1 X plus D by G X T. So now if we increase R, then we will see that so we see that the slope of this enriching operating line is equal to R by R plus 1, and then R is defined as L by D. Suppose if we return all the distillate back to the column, so that means actually D tends to 0. We are not drawing any product out. We are sending all the total condensate back to the column. So this means actually R tending to infinity. If this R tends to infinity, then Y becomes equal to X, meaning the enriching operating line will coincide with the 45-degree line. Okay, and this is what we call as a total reflex. So total reflex means returning all the condensate from the condenser to the distillation column. Under this condition, the enriching line, operating line, as well as the exhausting operating line, they both coincide with the 45-degree line. So it means that in general, for a finite reflex ratio, the enriching line and the exhausting line will have a particular slope. This is for some reflex ratio R. When we increase this reflex ratio R to very large value, R tending to infinity, what happens is that this two lines, the enriching line and the exhausting line, they actually lie on the 45-degree line itself. Okay, this basically corresponds to this will correspond to the minimum number of stages, because here the operating line and the equilibrium line are the farthest. If you look at this particular finite value of reflex ratio, the driving force for the mass transfer is these concentration differences between the equilibrium line and the operating line. But when we operate under total reflex, the operating line coincide with the 45-degree line, then we have the maximum driving force available for mass transfer. So this will lead to total reflex will lead to minimum number of stages. Minimum number of stages. So this can be shown pictorially here. So at a total reflex, which corresponds to sending all the condensate back to the distillation column and no product is taken out, will lead to the operating line merging with the 45-degree line. So this is the 45-degree line, and all the operating line, both enriching and exhausting operating line, coincide with this 45-degree line. So then we can find the number of equilibrium stages for distillation for a given XD and XW following the staircase construction. So we start at XD and then we go horizontally and then come vertically down to the 45-degree line, and then we continue this process. So this is stage 1, this is stage 2, and then stage 3, stage 4, and then we go all the way up to XW. So here you see that since both operating lines are coinciding with the 45-degree line, we don't have to make a transition between the two lines. They are the same in this particular case. So total reflex this leads to minimum number of theoretical stages. So in terms of operation, what it means is that at the condenser, it's a total condenser, so all the vapor is condensed and then the liquid condensate is sent back to the distillation column, whereas at the reboiler, all the liquid is vaporized and then sent to the column, and then the feed has to be close to zero. So that is the operation point of view. That is the operational conditions for ensuring total reflex. Now, this particular process of calculating minimum number of trays or minimum number of stages can be done graphically, but if the relative volatility is constant, we can also get an analytical expression for minimum number of theoretical stages. So we like to calculate so under total reflex and alpha is constant, analytical expression for minimum number of stages, n minimum. Now let's consider the reboiler. So so you can draw the reboiler something like this. So this is the reboiler. This is the bottom of the distillation column, and so here the liquid flow rate coming down from the column is L bar, and it has a composition, liquid composition of Xn, and then this entire liquid L bar is vaporized in the reboiler, because reboiler is also operating under this total reflex conditions. So this gas flow rate we say is G bar, and then the composition this vapor is YW, and we say that this condition is at saturated vapor condition. This is a saturated vapor. And here we are not withdrawing any residue here, all the liquid is vaporized in the reboiler and sent back. So now, since we said that the alpha, the relative volatility is constant for this system, we can actually use this definition of alpha, which is y by 1 minus y divided by x by 1 minus x, or in other words, y by 1 minus y is equal to alpha into x by 1 minus x. So this is basically the equilibrium relation for the binary system A and B that we have. Now the reboiler operates such a way that the YW is a saturated vapor. Corresponding to that, there will be a saturated liquid with a composition of XW. So we can write this equilibrium relationship for YW and XW. So this condition is satisfied at the reboiler. So remember here, YW is the composition of the saturated vapor and XW would be the composition of the last droplet that is present in the system. Okay, so here we said that reboiler vaporizes all the liquid into vapor. However, this is at the dew point, so you'll have the last liquid droplet, the rest of them are vapor. So if you have to show in terms of the TXY diagram, so this is T versus Y and this is T versus X, and this stream Xn is the composition of the liquid that is entering and at the bubble point. So let's say we identify that as somewhere here. Okay, so this corresponds to Xn. What we do here is in the reboiler, we take this liquid and then we vaporize completely up to this point, which is the dew point. So at this dew point, the composition is YW and the corresponding equilibrium composition of the liquid is XW. But since we are completely vaporizing all the vapor, the total system is vapor, and then there will be a small droplet of liquid corresponding to XW. This relationship between XW and YW is given by this. Okay, so this we understand, and we can also see from this figure that this since we are vaporizing all of them, this YW is also equal to Xn. YW is equal to Xn because we are vaporizing all the liquid. We are vaporizing all the liquid. So we are talking about three composition. The composition of the saturated liquid entering the reboiler at Xn, and this entire liquid is vaporized up to the dew point, and the vapor will have a composition of YW, and XW and YW are related by this relative volatility. Corresponding to YW, there is an equilibrium composition that is XW. Now you can see that in this diagram, YW is equal to Xn because we are vaporizing all of it. Instead of vaporizing all of it, suppose if I stop somewhere here, then we would have two-phase mixture containing vapor at this composition and liquid at this composition, but we are not doing it. In the reboiler, we are vaporizing all the liquid, so we go from here to here all the way. Okay, so that's why we say YW is equal to Xn. Now let's substitute this in this equation. So we say that Xn by 1 minus Xn is equal to alpha times XW by 1 minus XW, and we are able to write this only because we are operating under total reflex condition where the reboiler vaporizes all the liquid into vapor. So this condition is also true. This equation relates the relationship between Xn and XW. Now let's look at this application to the nth tray. So in the nth tray, let us draw the notations here. So this is nth tray, and the liquid that is leaving the nth tray is Xn, and the stream that is coming in is Xn minus 1, and the vapor that is entering here is Yn plus 1, and the one that is leaving is Yn. So since this is an ideal tray, Xn and Yn are in equilibrium. Which means that Yn must satisfy this condition, because we are assuming a constant relative volatility to relate the vapor and liquid compositions. And another thing we should note is that since the operating line is on the 45-degree line, the consequence of this is that yn plus 1 will be equal to xn. Generally, we obtain the relationship between yn plus 1 and xn based on the exhausting section operating line, but we know here under total reflex condition the operating line coincides with the 45-degree line, therefore yn plus 1 is equal to xn. So here you see that in this equation we can replace this xn from the above equation. So let us write here yn by 1 minus yn. This can be written as xn minus 1 by 1 minus xn minus 1, that is equal to alpha times this xn by 1 minus x1 is nothing but alpha times xw by 1 minus xw, alpha times xw by 1 minus xw. So that is you get alpha square times xw by 1 minus xw. This is the value of xn minus 1 by 1 minus xn minus 1. So like we have done for the nth tray, let us go to the one tray above, that is n minus 1th tray, and then write this set of equations n minus 1th tray. So this is n minus 1. The liquid that is leaving here is xn minus 1. The vapor that is leaving out is yn minus 1. The one that is coming here is xn minus 2, and this is yn. So here again the xn minus 1 and yn minus 1, they are in equilibrium. So we can say that yn minus 1 by 1 minus yn minus 1 should be equal to alpha times xn minus 1 by 1 minus xn minus 1. And we know this value for this from here. So if I substitute, you will get alpha cube times 1 minus xw by 1 minus xw. And we also know that this is the operating line corresponding to 45-degree line. So we will be able to write yn minus 1 as xn minus 2 by 1 minus xn minus 2. This is because we know that yn minus 1 is equal to xn minus 2. This is because the operating line is in the 45-degree line. So we can write this is equal to this, and then we get alpha cube into xw by 1 minus xw. Now, so if we continue this operation all the way to the first tray, we will be able to write that y1 minus 1 minus y1 is equal to xd by 1 minus xd, that is equal to alpha times x1 by 1 minus x1. And then if I replace this recursively, we will be able to write that xd by 1 minus xd is equal to alpha power n plus 1 times xw by 1 minus xw. So what we have done is, through this recursive relation and applying the equilibrium condition as well as the operating line of the 45-degree line, we are able to relate the distillate composition xt to the residue composition xw. So from here we can rewrite this equation as alpha times n plus 1 is xd into 1 minus xw by 1 minus xd times xw. And if you take logarithm of this, you will get ln of xt into 1 minus xw over xw into 1 minus xt over ln of alpha. and this is called the Fensky equation. The Fensky equation can be used for total reflex conditions and alpha is constant. Then Fensky equation gives the minimum number of ideal stages. So now we talked about the highest possible reflex, that's called total reflex. Then we asked the other question, can there be a minimum reflex ratio? Is there a minimum reflex ratio? Yes, there is. Let's open a figure here. And the concept of minimum reflex ratio can be illustrated with a diagram here. Suppose if you consider this case A. So we have the equilibrium line, we have the enriching operating line, and also the exhausting operating line. The feed composition, distillate composition, and the residue composition, these are all given. And you would have generally, if I have to take a different color, so yeah, for any finite reflex ratio, you would have an enriching operating line that cuts the Q line. So this is Q line, this is Q line here, and then there will be a corresponding stripping or the exhausting operating line. Now if we decrease the reflex ratio, the slope also decreases, and then you can keep on decreasing it all the way to the point N. Point N is at point N we have an intersection of the equilibrium line, the Q line, and all the operating line also, the enriching operating line. So what we are trying to say is that you decrease the slope all the way to reach the point N, where the enriching line meets the equilibrium line as well as the Q line, and this corresponds to the minimum reflex ratio. You cannot decrease reflex ratio below this, because if you go below this, you might reach a point somewhere here, and that is outside the equilibrium line. So the smallest reflex ratio you can use is the point that corresponds to N. Okay, so we construct so we obtain a minimum reflex ratio by drawing a enriching line such that it passes through the intersection of the Q line and the equilibrium line. That corresponds to the minimum reflex ratio. So what we are saying is that draw the enriching operating line such that it intersects the equilibrium and Q line at point N here. Okay, and this will intercept the intersection of this line would be xd by rm plus 1, and from here you can find what is the minimum reflex ratio. So this is the case if you have a well behaved equilibrium line. but sometimes we have an equilibrium line shown by this case B. In this case, based on this procedure, we may be actually tempted to draw a line that goes from here and then cuts this point K, and point K is the one where the Q line meets the equilibrium line. So we may be tempted to draw this line, but if you do this, you see that this line falls outside the equilibrium line, so this is not permitted. So what we need to do is, you start from the 45-degree line and then keep on increasing the slope. You come here and then go there and then go all the way where it just barely touches the equilibrium line. So in this case, you can see that the operating line that touches the equilibrium line at point P, not at K. Okay, so sometimes this getting the minimum reflex ratio is a lot to do with the shape of the equilibrium line itself. In this kind of a problem, it is very straightforward to draw the enriching line that goes through this intersection of Q line and operating line. But in cases where the equilibrium line is a little bit differently shaped, we have to draw the operating line corresponding to the minimum reflex ratio such that it just grazes over the equilibrium line somewhere here. Okay, so it depends on the local curvature also. Another possibility is here where the enriching line can be drawn connecting to this point T, so such that the Q line and the equilibrium line is at point T. So the enriching line can also go through this. So this is perfectly fine. However, at point T, the exhausting line should also go through. So then you are expecting the Q line, the operating line for the exhausting line to go like this. But this is not physically permitted because this operating line falls outside the equilibrium line. So here in this particular case, the minimum reflex ratio has to be obtained from the exhausting line. So here we start with the exhausting line at 45-degree line, and then we keep on increasing the slope all the way here where it just barely touches at this particular point, where this operating line touches the equilibrium line barely at this point. And then we extend this line and then cut the Q line, and in this point the enriching line will also go through. So then you draw the enriching line from here to here and then extend all the way here. So in this particular case, the minimum reflex ratio is not directly obtained from the enriching operating line because the curvature of the equilibrium line is quite different here. Okay, so here what we are trying to say is that you slowly increase the slope of the exhausting operating line until it touches the equilibrium line at this point, and then extend this line to touch the Q line. Then you mark this point, let's say point A, and we know that the exhausting line should also go through this point A because we know Q line is the locus of points where both lines touch each other or intersect each other. So now, having known this particular point A and we know XD, and then we can draw the operating line for the exhausting line and then extend to the intercept, and this will give you the minimum reflex ratio. So to summarize, obtaining the minimum reflex ratio means drawing the operating line with the smallest slope possible so that it touches the equilibrium line. For regular equilibrium line like this, where alpha is nearly constant, it is a straightforward process. All we need to do is we locate XD, we locate XF and then draw the Q line, and then we locate the XW. Then we look at the point N, which is the intersection of the Q line and the equilibrium line, and then we draw the enriching line from M through N all the way to the intercept. And by reading the intercept value and equating that to XD by Rm plus 1, we can find the minimum reflex ratio. So minimum reflex ratio corresponds to infinite number of theoretical stages, because in this case, if I start drawing the number of stages, you see that as I go to close to point N, the driving force vanishes. So the number of equilibrium stages would go to infinity. Okay, so the consequence of operating the distillation column under a minimum reflex ratio would mean that the number of theoretical stages are infinite. Now, for cases like this, where the equilibrium line is differently shaped, we cannot just directly take the intersection point between the Q line and equilibrium line and connect with the enriching line, but rather we start with this 45-degree line and then slowly increase the slope such that it meets the equilibrium line at point P, and then we extend this point all the way to the intercept, and from here we read the minimum reflex ratio. In some other cases where you have the equilibrium line, so in other cases the minimum reflex ratio has to be obtained from considering the exhausting line operating conditions. So in this case, what we do here is we start with the exhausting line at 45-degree line and then increase the slope such a way that it goes through this, it touches this equilibrium line at this point, and then extend this line to the Q line, and this meets at point A, and then we connect point A and XD here, and then extend this line beyond, and then you get the minimum reflex ratio from here. So what we are saying is that we looked at two limits. One is this total reflex, which means R goes to infinity, whereas N is N minimum, the number of stages is minimum. And another one is minimum reflex, where R is equal to R minimum, where N goes to infinity. Okay, so these basically gives us two extreme limits of operating the distillation column. Operating under total reflex means we operate under minimum number of theoretical stages, but we are not able to withdraw any product. On the other hand, under minimum reflex, we have very large number of theoretical stages, the N going to infinity. So we can ask, what about the optimum reflex ratio? Is there an optimum reflex ratio? So generally, what happens is that the optimum reflex ratio has to be obtained based on economics, the cost involved. So if I have to plot the number of stages as a function of reflex ratio corresponding to R minimum, the number of stages goes to infinity, whereas when R goes to infinity, the number becomes minimum. So you expect the number of stages to go like this. When R is R minimum, this goes to infinity. When R goes to infinity, N reaches N minimum value. So that's a compromise that we have to do. So if you operate at minimum reflex ratio, the number of stages are infinite, and if you operate the column at infinite reflex ratio, the number of stages are minimum. It actually means that the cost is related to the reflex ratio. So generally what happens is that, so this is the one corresponding to R minimum. So the fixed cost or the capital cost typically goes something like this, where when R is R minimum, the number of stages are infinite, so the cost involved in setting up a very large column will be also very high, and as we increase the reflex ratio, the cost comes down, reaches minimum and then goes up. Whereas in terms of operating cost, which means cost involved in heating, cooling requirements and utility, it kind of steadily increases with reflex ratio. If we draw the total cost, it will go something like this with a minimum, and this is what we call it as a R optimum. So generally R optimum will be about 1.2 to 1.5 times R minimum. So the value of R minimum kind of gives a indication what should be the optimal reflex ratio to use. Now so far the continuous distillation column design involves the calculation of ideal stages or theoretical stages, but we also have to invoke the concept of tray efficiency, because the trays in reality are not ideal. So we can define an overall tray efficiency as number of ideal stages over number of real stages. So the calculation of overall tray efficiency is little bit tricky and quite involved in terms of calculations, but there are empirical data available, like we discussed in the case of absorption column tray efficiency. There are plots that relate the overall efficiency with alpha times mu, where alpha is the relative volatility and mu is the viscosity of the liquid, and you see some sort of an empirical correlation, and we can look at the relative volatility and the liquid viscosity, and then from here we can read the overall tray efficiencies from empirical data set like this. And once we know the efficiency, using this definition of overall efficiency, we can calculate what is the real number of real stages. So it involves basically two stages. First stage is to calculate the number of ideal stages. After that, we obtain the efficiency separately from empirical correlations, and using that we can calculate the number of real stages.